All right. Related rates, and you're never going to believe this, but related rates is about rates that are related. So, boom, done. We did it. All right. So the problem that this is going to look like, what these are going to look like is that you are going to be given the rate of one thing, and you are going to use it to solve for the rate of another thing. And we're going to do that using one rate to solve for another rate using derivatives. And in fact, we're going to be using implicit differentiation to do it, where we like write our dy dx's and all that good stuff. So that's how we're going to get our rates written in terms of each other. So here come our steps to solve. Identify all the given quantities and the quantities to be determined. So just like any word problem, you're going to write down the things you know and write down the things you're trying to solve for. Some of them, it might help to make a drawing or a diagram for some of these problems. Then you're going to write an equation involving the variables. Usually this is going to be some, maybe some type of geometric formula or some formula that they give you in the problem. Any of those kind of things are equations that you could write that would be helpful here. Using the chain rule and really implicit differentiation, differentiate both sides with respect to time. So we are going to be looking at how these rates are changing over time. After differentiating with respect to t, substitute everything that you know to solve for the thing that you're trying to find. And usually the thing that we're trying to find is a rate. And then the last step that I wrote in here is check your units. Make sure that you're writing in terms of units. It's usually going to be like something per second or something per minute. And just make sure that those rates are correct. So let's look at a couple of examples. We'll start with some basic ones to give us an idea of how they work. And we'll move into more complicated territory here as we go along. Edges of a cube are expanding at a rate of 3 centimeters per second. How fast is the volume changing when each edge is 1 centimeter and 10 centimeters? So you can imagine this cube kind of expanding outwards. And we are looking at the sides of the cube. That's the thing we're controlling. And as the sides of the cube get bigger, the volume is going to get bigger. But it's not going to get bigger at the same rate that the side gets bigger. Right? Because if the side goes from 2 inches to 3 inches, the volume doesn't go up by 1. It goes up by a lot more than that in a cube. So we're using the rate of change of the side to solve for the rate of change of the volume. How fast is the volume changing? So we are trying to find dV dt. We're finding the rate of change of the volume with respect to time. And I'm going to go ahead and write that since we want to know about volume, let's write down volume of a cube gets the side cubed. That's why we call it cubing, because it would be the volume of a cube with that side length. That's why it's called cubing. And what we are given here is that ds dt, in other words, the rate that the sides are changing, is 3 centimeters per second. That is ds dt. So we're using that rate for the sides to solve for the rate of the volume. Rates that are related. So now we go on and we take the derivative. By the way, this is a positive rate because the sides are expanding. They're getting bigger. Sometimes you'll see the rate of change be negative if something is getting smaller. So that's something that we'll have to think about going forward. But for this one, it's just getting bigger, so our ds dt is positive. So let's do our derivative here. Derivative of v is 1 dv dt. We're taking all these derivatives with respect to time. So any variable we're taking the derivative of, we need to put it in terms with a dt on there. Equals derivative of s cubed is 3s squared. And then that's going to be ds dt. We're going to write a ds dt. Again, in our notation here, that is how much s is changing with respect to time. So now we can solve the problem. Part A. Part A says s equals 1 centimeter. So let's plug in everything we know here. dv dt equals, well, it's going to be 3s squared times ds dt. Well, our s here in this case is 1. And our ds dt was 3. So we're going to put in 3 for ds dt. And that's going to equal 1 squared is 1. And then we have 3 times 3 is 9. And our units should be centimeters cubed per second. Right? Because it's a rate, the volume is changing over time. Centimeters cubed per second. And you can double check that that's how the units are going to work out. I have centimeters that I'm plugging in here, so I'm squaring centimeters. There's centimeters squared. And then I'm multiplying by this 3, which is in centimeters per second. So centimeters squared times centimeters per second is centimeters cubed per second. And the units work out the way they're supposed to. But now, part B, let's look at what happens with this rate when s is 10 centimeters. Should this answer be bigger or smaller than part A? Bigger. Because if I have a larger cube expanding at the same rate, the volume is changing a whole lot faster. So dv dt here, let's put our function in again. Squared times our ds dt. Well, our ds dt is still 3. Side legs are still expanding at the same rate. But this time, our s is 10. And we get 10 squared is 100 times 3 times 3. That's going to be 900 centimeters cubed per second. So when I change the side length, I haven't changed the rate that the sides are going up, but I have changed how big the cube is that we're looking at. And now that, that rate of the volume goes up. All right? That should have been a pretty easy one. Let's look at our next one here. And I want to give you a minute here on this one to do your first step. So in other words, I want you to write down the given quantities and the quantities to be determined. Figure out what rate you're trying to find and what information it's already given you. What is that 4.5? What is the 2? And how do we write what we're trying to solve for? This one will be a little bit trickier because we'll actually have to solve an equation. What are we finding? Okay, so dr dt. Oh, radius, when the radius is 2 feet, so r equals 2. And then we are told something is 4.5. What is the 4.5? It is, and the clue that it is this dv dt is that the rate, well, first off, the amount of air in a balloon is a volume question. That's your first clue. Your second clue is that it's in cubic feet per minute. Well, if we're in cubic feet per minute, then that should be a rate of change of a volume, since volumes are in units cubed. Okay, so we know dV dt, we know r, we're trying to find dr dt. So let's write an equation that involves a volume of a sphere with the radius and the volume of a sphere I should note here that surface area and volume formulas tend to be given to you. If they want you to use like the surface area of a cylinder, they're going to just tell you what the surface area of a cylinder is. You will not need to go back and memorize all these geometry, surface area, and volume formulas. It will tell you, hey, here's the volume of a cone. We want you to use it to find different rates of change. They will not give you things like some problems will ask you about sine, cosine, and tangent. You'll need to know those, of course. Some problems will ask you to use Pythagorean Theorem. You'll need to know that. Plain old area formulas like area of a circle, area of a square, any of those, you'll have to know. But surface area and volume formulas, they're going to give you. So you would be given, recall the volume of a sphere is 4/3 pi r cubed. And you'll be like, yes, I do recall that. Time for the derivative. Derivative of v is dv dt. Four thirds pi times derivative of r cubed is 3r squared. So in other words, 3's cancel, and I have 4 pi r squared. dr dt. I took a derivative of r, so I need a dr dt. And we are trying to solve for dr dt. So we're going to plug in everything else and use that to solve for dr dt. Here we go. R squared dr dt. And we also have dv dt. Well, dv dt is 4.5. And then we are also told that r is 2. I'm going to leave this in terms of pi. I'm not going to get a decimal out here. 2 squared is 4, so 4 times 4 is 16 pi. So dr dt, 4.5 over 16 pi. And that's going to be, what were our units here? We're double checking our units. Feet per minute. It was cubic feet per minute, and so dr dt is going to be in feet per minute. Questions so far? Hopefully we're still on board. Okay. Yes. Good. Good. All right. Let's continue then. I'm going to skip this one and come back to it tomorrow. I'm actually going to start class tomorrow by having you try this one yourself. All right. We have our absolute classic geometry problem where a ladder is leaning up against a wall. A ladder 20 feet long leans against a building. All right, let's see here. Here's a building. Huh? Why would you need a door? No, they just have building written on them. Yeah. We see the ladder on the side of the building. We don't need to get into the building.
Can we make a cross section of the ladder going this way? Is that how that can work?
Oh, like
Yeah, like going back.
like that? Yeah, that's what would make sense. Okay.
Just try to use what you taught us.
All right, here's my ladder. I'm going to call I'm going to use L as a variable for the ladder. Cursive L so you don't mistake it for 1. And then I'm going to have this distance right here. I'm going to label X. And the height of the building I'm going to label as H for height. Height of the building. I don't see any angles there, so it looks like it's time for Pythagorean Theorem. L squared equals X squared plus H squared. And I'm just going to jump to looking at the derivative here and talking through that part of it. Derivative of L squared is going to be 2L times dL dt. Derivative of X squared is going to be 2X dx dt. Derivative of H squared is 2H dH dt. And just to make this easier, since these all have a 2 out in front of them, let's divide this whole equation by 2. And what I want you to do here is let's write down all the information that we know. We have L dL dt, we have X dx dt, we have H dH dt. So that's 6 different variables here that we need to keep straight. So my hope is that we know 5, and we're trying to solve for the 6th thing. So write down what each of those are. Which rate are we trying to find? Between dl dt, dx dt, and dh dt. Give you 1 minute. There's 3 numbers sitting in front of us, so those should be easy to get. Which ones are which? You need to figure out the one thing that you're trying to solve for, and then we have 2 more quantities that we need to know. So you'll have to think about how to get them or how to figure them out a little bit. So this is where I'm making it slightly more complicated. We got more variables going on. Not everything is given plainly out in front of you. Some of it is left for you to determine. This answer I will go ahead and round once we get there. I will show the exact answer, but I will also round it. All right, let me write down the easy ones first. The ladder's 20 feet. What is 8? Which one is 8? It's the height. So how do we know what x is? Just do Pythagorean Theorem. We know 2 sides. We're trying to find the third, so we're going to do, our hypotenuse here is 20. And we're trying to figure out what x is. And I could, there you go. You know how to do Pythagorean Theorem. I don't need to show that. Square root of 336. Feet. Again, I will round that at the end. All right, we have 3 rates here. Which rate are we trying to find? How fast is the ladder sliding down the house? So dh dt is what we're trying to solve for. Which one is 4? It is dx dt. What is dl dt? What does it represent? The rate of change of the ladder's length. It doesn't change. In other words, dl dt is 0. The ladder is always going to be 20 feet. It's not suddenly going to shrink unless it, it's not going to snap in half as it slides down the building or something. Okay? So we plug all those in. 20 times 0 equals x is square root of 336 times dx dt is 4 plus h is 8 times dh dt, which is what we're trying to solve for to begin with. And then something's going to happen here. Let's see. 0 equals 4 square root of 336 plus 8 dh dt. Move the 4 square root of 336 to the other side. And then when we divide by 8, dh dt is going to be 4 over 8 is 1/2, so negative square root of 336 over 2, which rounds to negative 9.165 feet per second. So what I want to point out here is that this dh dt here is negative. Why is it negative? Because we are sliding down the building. And if we're sliding down the building, the rate of change of the height should be negative. It should be getting more down the building. And dx dt was positive because it was going away from the building. So the distance the ladder was away from the building was going up. The height was going down, so that rate was negative. Okay? 1 second. Let me